Hey everybody, time for the next semester of math, Math 3A, Calculus. So again, I'm taking this class at IVC. I'm not an instructor, I'm just taking the class as a student, and by way of helping me learn the content, I am posting questions that are given to us in class, working them out, so maybe it can help some of you guys as well. So again, if you have questions, I encourage you to talk to your instructor. As I go through the video, I encourage you to stop the video when you see the problem, try and work it out for yourself, and then watch the video to see how I work it out and see if we come up with the same solution. If I make small mistakes, please put them in the comments below. I will do my best to respond to everyone that posts. And yeah, so let's get started. This video will be on chapters 1 and 2 of our book. And it leads us up to the first test that I'll be taking in my class. May not be the same test segment as your class, but anyway, without further ado, let's get started. So for this first problem, we sketch the graph of each equation, identify any intercepts, and test for symmetry. And letter A here, we have y squared equals x plus 4. And you might remember if we have the y squared as opposed to the x squared, we have a parabola that is off to the side here. And since it's a positive y, it's to the right. It opens, rather, to the right. And this plus 4 means that it's going to be shifted to the left 4. So you might just remember that this is the graph that we are kind of should expect. A parabola opening to the right, shifted over 4. Um, or we can do it mathematically. We can show that y is equal to plus or minus the square root of x plus 4. We can look for our x-intercepts. I'll just use this y plus or minus square root of x plus 4. The y-intercepts of this would be, we'll put the square root of x plus 4 is equal to 0. Now, of course, I could have done this with the original problem, the y squared equals x plus 4. But anyway, so we have x plus 4 is equal to 0, and then x equals negative 4. So this is how we get the coordinate negative 4, 0, and that's our only x-intercept. And that's what I already said before by just doing transformations of the original problem. So our y-intercepts, again, it's plus or minus the x plus 4, or square root of x plus 4. So we have plus or minus 0, replacing that x with a 0, because we want to find y-intercepts. So 0 plus 4 equals y. And so then we get plus or minus square root of 4 equals y. So that gives us plus or minus 2 equals y. So that means we're going to have two coordinates. We're going to have a plus coordinate and a negative y coordinate. So we have 0, positive 2, and 0, negative 2, which is basically what we saw in my rough sketch before. But now let's get more specific. You can see 2 here and 2 here. I didn't sketch it very well, but now we're being more precise. So I'll make those marks, and then there you go. There's our graph of this equation. And we've identified all of the intercepts as well. So this is, if you remember a square root function, you know it looks like this. This is a square root function. And since we translated it 4, that means we move it to the left. This is another way you might remember this type of graph. That's the plus version. Now, the minus version of that would be uh, a reflection, basically. That minus in the front would make it a reflection. So that means it would reflect over the x-axis, so you get the other half. So there's 3 ways that you could have graphed this. You could have just remembered from memory uh, that y squared equals x plus b, which is kind of how that one works. Or you could have looked for all the intercepts as we did before. Or you could have used just your knowledge of the square root function. So knowledge of, wow, my penmanship is terrible today. Square root function. And this next problem is very much similar. If you have knowledge of f of x equals the absolute value of x, you know this is kind of a v pointing up at the origin. So just rough sketch here. Just this is what it would look like. And since we have this minus 3 here, that means it's going to shift down 3 units. So we're going to have this, again, this is just a sketch. This is the line we would really have. And it's asking for our x-intercepts and y-intercepts, so we might as well just check for those. So we have our x-intercepts and our y-intercepts. So to find our x-intercepts, we just sub in 0 for y and then solve. So we have the absolute value of x minus 3 equals 0. Move that 3 over. We have the absolute value of x equals 3. And there's only one number that satisfies, well, there's actually two numbers that satisfy that. That's plus or minus 3. So we're going to get an ordered pair of negative 3, 0. And we get 3 and 0. So when to do our y-intercepts, we just substitute 0 for x. So we have 0 minus 3, absolute value of 0, which is 0. Minus 3 equals y, and then negative 3 equals y. So, whoops, why did I say negative 30? Our ordered pair is 0 minus 3. So, and we saw that from this translation down 3, so we knew that that was there. And then we'll just plot these two, which I was much better at sketching this graph because I knew it was a line anyway that was slope of 1 or negative 1 on this side. So there you have that. On to number C, or letter C rather. We have y equals x to the third minus 2. Now, an x to the third graph looks something like this, but we are transitioning this whole graph down too, so my sketch would kind of look, my rough sketch would look something like this. But I'm terrible at sketching these graphs with curves. But anyway, again, it was asking for our x-intercepts and our y-intercepts. So here we go. We've got substituting a 0 for y. So 0 equals x cubed minus 2. So now we have 2x cubed. And now we have the third root of 2 is equal to x. So our ordered pair is third root of 2 comma 0. And third root of 2 is like something just a little past 1. So y is our y-intercepts rather, putting 0 in for x, and we work out to 0 comma negative 2, which is what we said before, just using the translation rules. Now, again, this third root of 2, I'm going to use a calculator. I don't have any of that stuff memorized. So we only have one x-intercept somewhere right about there, just past the 1. And so our graph would somewhat look like this. Got a little extra leg on that one. Same thing for the top. But anyway, there you go. So there was another question, part of this question in the original problem, and it asked about symmetry. So I'm going to go back and do those for all three of these. This is not not symmetric to the x or y axis or the origin. So make sure we add this statement in so we get full credit for these questions. And box that one up. We'll go up to B here. This one is symmetric, but only about the y-axis. So you can see it only reflects across this axis right here in the middle. So we'll just write that statement, symmetric. about the y-axis. And we'll go back to letter A. Ugh, this one was messy. Now this one is only symmetric about the x-axis. As you can see, it reflects right through the middle here. So that's the x-axis. So we'll just write symmetric through the x-axis, or symmetric about the x-axis. So there you go. So for these next ones, we need to sketch the graph of each equation. Pretty easy. For this one, we want to remember the line, yes, or sorry, the y equals mx plus b. This is the equation for a line. So we just turn this into that form by shifting over that 6. And then we are going to shift over the 2x. So we're going to get 3y equals negative 2x plus 6. And then we're going to divide that whole thing by 3. So we're going to have negative 2/3 x plus 2. Now, we are in the standard form for, or it's easier to put this line on with this form. So our y-intercept is plus 2, so I can just sketch that. And then I can use the slope, which is the m. I can go down 2 and over 3. I get the other coordinate. And then, so we got 0, 2 here, and then we got 3, 0 here. Those are basically our intercepts. And we just sketch this line right through here. Dun, 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 dun. Put my arrows on the end, and there's our first graph sketched. Pretty simple. B is x equals a negative 3. Well, this is going to be a vertical line. So we go over to negative 3 and draw a vertical line because there's no y-intercepts. So that means there's no slope, and there's also no slope. So there we go. We got a vertical line. This coordinate is negative 3, 0, and then we can just call this line x equals negative 3. So pretty simple on that guy. And then for this one, y minus 4 equals 0. We'll just move that 4 over and make it a positive, so we're adding 4 to both sides. So we get y equals 4. So we go up 4, draw a horizontal line because there are no x-intercepts. And there you go. Label this point 0, 4. Oops. Sorry about that. And there you go. That's that. So these next to 3, we're going to evaluate the function f of x equals 3x squared minus 2x plus 6 at the given values of the independent variables. Simplify your results. So here we're just going to sub in the negative 4 to our function. So here we go. Write this down, plus 6. There we go. And then 4 squared, that's going to be 16. So 3 times 16 minus negative 2, well, 2 times negative 4, that's going to be negative 8, plus 6, there we go. Now, 3 times 16, that's going to give me 48. And these two negatives cancel, we get a positive, positive 8 plus 6. 48 plus 8 is 56, plus the 6. And then those together, 72, wait, not 72. What am I thinking? Erase that. 62. Try to add another. I'm stuck on this 72 thing. Focus. 6. There we go. 62. All right. There's that one. Move on to this one. This one's a little more complicated because we're substituting this 2a minus b, but we can do it. Squared minus 2 times quantity 2a minus b. And then we'll throw on the plus 6 on the end here. And I'm just going to do a little quick side work for this second section here. So Sometimes I just can't FOIL in my head. I just have to write it out this way. But here we go, 4a squared, and then we have two negatives, so this is still going to be minus 4ab plus b squared. There we go. So we've got 3 times the quantity of all that crap I just did on the side. So I'll transpose all of this over here, plus b squared, and then minus. I guess I could distribute this. So 4a plus 2b plus 6. And I need to distribute that 3. I guess I could have done that first as well as I transcribed it, but anyway, 12a squared minus 12ab plus 3b squared. And then we have the rest of this junk that we had from before. And there is our answer for B. So put a little box around that guy. And then on to letter C. Oh boy, this is where it starts getting a little hairy. But basically, I'm going to take this x plus h and I'm put it in both these places. And then I'm going to take this x and I'm going to put it into the original function. And basically, it's in these 2 points as well. So let's start off with that first part of the function. So we'll do 3 and then x plus h, and that's squared, minus 2, and then the x plus h, plus 6, minus, so we've done this first section, we put that into that function, and that's that part of it. Now we're going to do this part. So basically, it's just writing that original function, but inside parentheses here. This is the important part of this. You must put this parenthesis here because you're going to have to distribute that negative. You're just going to change the signs later. So anyway, here's that half of that function. Now this is all, of course, over h, which is this h right here. So what to do next? Well, we're going to FOIL out our this part of it here. If you can do it in your head, you can, but I'll just do it on the side here just so you can see. Get x squared plus 2xh minus h squared. So I can rewrite that over here. So 3 times the quantity of x squared plus 2xh plus h squared. Then plus, I'm sorry, minus, distribute that out. Well, I'll just not distribute it quite yet. Let's just write it all down together. We'll do the distributing all on the same function, or same step rather. There we go. And this is all over h. That looks a lot nicer. All right, so now I'm going to start doing my distribution. Distribute for each of these things. Doop, doop. So we end up with 3x squared plus 6xh plus 3 arms minus 2x plus h x minus 2h plus 6. Distribute this negative, so negative 3x squared plus 2x minus 6 all over h-ola. Remember to distribute this negative here. So you change all the signs in this last part. Mark it in a different color here. Remember, remember, remember. So all of this over h. So now I can start canceling or combining like terms, which will end up canceling some of these bits. So we have 3x squareds cancel. Let's see, what else do we have that cancels? Well, I messed this up. This was supposed to be, I'm distributing this 3, not a 6, so it should be 3. Oops. Let's get it in the right color. Should be a 3. There we go. That looks better. So this negative 2x and this positive 2x cancel out with each other. And of course, this 6 and the negative 6 are going to cancel with each other. So now I have something a little nicer. So 6xh plus 3h squared minus 2h all over h. Now I can cancel out these h's, and I'm going to get something even nicer, which is 6x plus 3h minus 2. And that's my final answer. A lot of steps, but there you go. So for these next few, we need to find the domain and the range of each function. Well, our exponential function looks like this. Exponential. Our square root function looks like this. We're going to translate it to the right 2, and we're going to reflect it over the x-axis. So basically, this is a rough sketch of our graph. So we can write our domain off of this. We don't need to be super precise because this will be pretty easy. But our domain is 2, and we're going to include the 2 to infinity. And then our range is negative infinity and all the way up to 0. And we include that 0. So negative infinity. And we're up to 0. So that is our vertical part of it. On to letter B. Well, B, we can do a rough sketch of this guy. X can't equal negative 3 because that would make the denominator 0. So we can sketch a vertical asymptote at 3, or sorry, negative 3. And so we can look for x. There's going to be a horizontal asymptote at x. I already know that. So we'll look for a y-intercept to find out which way this graph kind of goes, if it's positive on the positive side or the negative side. I can just sub in 0 for x, and we are going to find that we have intercept at 5/3. So 0 5/3, which is just over 1, but not quite to 2. So there's that. So we have a graph that looks something like this. There we go. So our domain is going to be negative infinity to negative 3. Yeah, right, both of these, domain and range. So we have negative infinity to negative 3, like I said before, and then our little union sign, and then we get it negative 3 to infinity because of vertical asymptote. And then our range is going to go up to our horizontal asymptote. So we have negative infinity to 0, but not included, union. And then we have 0 to infinity. Yay. All right, and then on to C. So now we have something that's a little more complicated. Now remember, cosecant is related to sine in this way. It's 1 over sine. So just for a little bit of help with this, because I have trouble just knowing exactly how to draw cosecant all the time, I'm going to draw one period of sine. I'm just going to sketch that roughly. Use some dotted lines here. Now, I haven't labeled these tick marks because we are going to obviously be doing some sort of translation with this function. But basically, we have these vertical asymptotes. This would be because we are looking at cosecant rather than sine. That happens everywhere where sine crosses the x-axis or at the zeros. So this is what cosecant would look like over one period. And we can just draw in a couple more vertical asymptotes here. And we can continue to sketch a couple more half cycles or cycles of our cosecant. Oop, wait, not all the way up to the x. It's only up to 1 because sine is between 1 and -1. So cosecant would go down to 1 and up to -1. So anyway, here's 2 cycles of cosecant. Now let's deal with this business so we can kind of label how far our asymptotes are apart, which is important to know because we need to know the domain. So we've done some sort of stretch or shrink. In this case, we've stretched it. So we need to know by how far. So the period of sine, is 0 is less than or equal to sine less than or equal to 2 pi. Now, we're just going to replace the sine part with this business, which was pi over x divided by 2. I'm sorry, pi x over 2. So we'll just put that inside here. And then we're just going to move everything out of the middle till we have x only in the middle. So if we multiply both sides by 2, we still get 0 on this side. And on this side, we're going to get 4 pi. Now we're going to divide everything by pi. And on this side, we'll still get 0. But we'll have x all by itself in the middle. And then on this side, we'll end up with 4 pi over pi. The pi's cancel. So we end up with 4. So our period goes from 0 to 4. So our period is 4. Now, if we divide 4 by our 4 tick marks, we end up getting a tick mark every single unit. So this is 1, this is 2, this is 3, and this is 4. So I'll redo this in black so you can actually see the numbers here, kind of in a sea of blue. There you go. Looks a little better, but not perfect. Anyway, we can see that every 2 units we have a vertical asymptote. So our domain, domain is x such that x cannot equal 2 k. Let me move this. I'm running out of room. Move it over here. Where k is a set of real numbers. I'm new to this type of notation as far as this e thing and then this z with a double line in the middle. I think that's the way you say it though. And our range, as I said before, I don't know how to do this in set builder notation, but in interval notation, it would be negative infinity up to 1, not included, and then, of course, 1 to infinity. So there you go, the box. All right. Now we need to evaluate the function as indicated, determine its domain and range. All right. Well, we have the square root function, which normally looks like this, but since we have this plus 4, we're going to move left 4. So we have our square root function here. And let's find a y-intercept. So we'll just do this little side work real quick. Square root of 4. So we have 2. And then that gives us a ordered pair of 0, 2. So we'll sketch that. And then we are going to have, this is what our, basically what our square root function would look like. However, we have this spot here that says, hey, you can only go out to 5, include 5, which is the x is less than or equal to 5. So let's put x is equal to 5. We end up with the square root of 9, which is 3. So our ordered pair is 5, 3. So I'll erase that guy. And I'll go over 5 and up 3. And up 3. Okay. So the top part of our piecewise function looks like this. And it's a closed circle because it's less than or equal to. So that's all we get for that guy. Now let's look at this other part of the piecewise function. Basically, we have a parabola at x equals 5 because we're going to the right 5 units, but we only want the part that is like greater than 5. So we only want this right side of this parabola. And that looks like a devil's fork. I don't know why I do that, but anyway. So we're only going to get this side of the parabola. Let's plug in some digits here, and we'll find out where, get a little more accurate on our graph. Let's try 9. I think 9 is going to be something that helps us here. 9 minus 5 is going to be 4, so 4 squared is 16. And that means I need to get rid of this stuff. I'll move it off to the side because our parabola is going to run it over. So count over 9. So this was 5 here. 6, 7, 8, 9. And then we'll go 16. And 16 is right there. So now we have a line here. So and that one goes on forever. So I'll mark this as 916. It's a nice little point. All right, so let's look at evaluating each of these functions. I'll mark the rest of these points as well. So we have a uh, f of -3. Actually, let's write our domain before I forget, because I did that earlier. I forgot to do this kind of step since it's asking for this. We can write the domain already because we already know it. It's -4 included to infinity because the blue line goes on forever, that infinity portion of this section, so we could get values all the way up forever. The y's would be really, really big though. And our range is 0 included all the way up to infinity. So that's the vertical part of this graph. That's this guy, right? So we'll get rid of this. We'll get rid of this, clean all this up, get rid of the devil's fork. There we go. Clean this up so it looks a little better. All right, so now we can start looking at these, evaluating the functions. And since -3 is certainly less than 5, we're going to use this function. So we'll just plug in -3 into the function, and lo and behold, we get 1. So -3 plus 4 gives us 1, and the square root of 1 is 1. So 0 is definitely less than 5, so we'll plug that in, and we get 2. And 5 is certainly less than or equal to 5, so we're still going to use that first function. So we'll plug in 5. We're going to get 9. Square root of 9 is 3, which we actually used that point to find where our function ended. So there's 3. And now we're on to f of 9. Now we're going to use the second one because that is greater than 5. So we'll plug in 9, which we use that as well to define our half of parabola, I guess you could say. So we know that this is going to equal 16. What am I doing here? 9 minus 5 squared. There we go. Trying to talk and write at the same time, and I just wrote the other function. So Anyway, so this is 16. So there you go, which was the same as that guy over there. So somewhat complicated, but we made it through. There we go. Okay, so here the graph of y of f of x is given. Sketch the graph of each of the following transformations. Well, here we have f of x plus 2. This is a transformation to the left 2 units. So I am going to just move these points. I picked some points where this function they gave us crossed over an intersection, so I'm just going to use those points. I'm just going to move those all left 2 units. Then I'm going to redraw the graph. And there you go. A is done. That's the first one. So now we'll look at B, and we have some craziness going on here. We've got a reflection right out at the front. When you're doing these transformations, doing the reflections first is usually the best idea. So since it's way out front, we're reflecting about the x-axis. So nothing happens with the ones that are on the x, but here are the points for all of these guys. Now, these aren't the final answer because we have this translation up 3. So I'm just going to move all of these dots up 3 units. This went up 3 units. These end up being on the x-axis now. And I guess I can redraw my graph here. And this is not the best, but you get the idea. These are rough sketches. They're not asking for exact values. And then for C, this is the last one. This one, we need to reflect across the y-axis because the negative is inside the parentheses. So I'm just counting the direction of way these points are from the y-axis and reflecting this business. But then we also have this, so that was a reflection, that was this negative inside. Now the negative outside is moving this up or down. So since it's negative, it's going to move it down. So I'm going to move all these down 1 unit, which will get me a parabola. I'm going to erase some of the other ones, the reflection part. And then we get a parabola that looks somewhat like this. So there you go. That's that one done. All right, for this next couple, we're going to do composite functions. We need to find f of g and g of f of x, given the domain of each composite function. And so to do f of g of x, and our instructor says rewrite this as f and g of x. So then you kind of see the order of operations. We're going to do the g into the f. So first off, we know that x needs to be greater than or equal to 2, because if we have anything less than 0 in here, we will have an imaginary number. So this cannot be negative. So that's why that exists. So now we're going to just plug that into our f function. So that's squared plus 4. Now we just reduce this, or simplify rather. The squared is going to cancel out the square root sign, so we end up with x plus 2. So the composite of f of g of x is equal to x plus 2. Now, trying to figure out the best way to where to write all this stuff. F of g of x equals x plus 2, and the domain is x such that x, run out of room, is greater than or equal to 2, which was that thing that we had over here. All right. Now we need to do g composed of f of x. And then rewriting that, we have f of g of x. Or I'm sorry, g of f of x. There we go. So now I'm going to take this other function and I'm going to put it this direction. I'm going to put this inside of that. Now, we can plug anything we want into x squared plus 4. So we don't have to worry about zeros there. So I'll just plug this all into this guy. Now this function is going to reduce down to x squared plus 2 under the radical. And that's it. Now since we have squared, x squared, it can be negative or positive. So really our domain is going to be anything. We don't. That's not going to make it a 0 really. So any number, even if it's negative, would still result in a positive value underneath the radical. So we'll put this over here, rewrite g composed of f of x is equal to a radical x squared plus 2, and the domain is basically all real numbers. So there you go. Put a box around that guy. All right, now we'll move on to B. This one gets a little bit more complicated, but we can do it. F composed of G of X. So I'm going to write this over here on this side, and then we'll do all our work horizontally here. Hopefully we can fit it in. So X cannot equal 5 halves. So 5 halves would make this denominator 0. So X can't equal that. Let's see if there's something else X can't equal after we compose this into F, or put this into F. So we have 2 times X plus 4 over X, 2X minus 5 minus 1, and then all of that over X plus 4 over 2X minus 5, and then that minus 2. I don't like working with fractions, so I'm just going to multiply the top and the bottom by 2x minus 5, which will clear all of my fractions. So that is going to give me 2x plus 4 on the top minus the quantity x, I'm sorry, 2x minus 5. There we go. And then on the bottom, I'm going to get x plus 4 minus 2x, or 2 times 2x minus 5. There we go. So what to do next? Well, we can distribute everything, and then we can collect like terms. So we have 2x plus 4 minus 2x plus 5. So we're distributing that negative. And on the bottom, we have x plus 4 minus 4x. Uh, Getting ahead of myself. Minus 4x plus 10. There we go. Now we can collect like terms in this nasty business. So on the, let's see, on the bottom, we're going to end up with negative 3x plus 14. We have a 4 and a plus 10. Yeah, so that's going to be plus 14. All right, and then let's combine on the top. We have a 2x and a minus 2x. That cancels that out. So now we have just an 8 and a 5 left together, so that's 13. 13 on the top. All right. So that means we have a 13, 3x plus 14. So the only thing that could really mess this up would be a 14 over 3. So x can't equal 14 over 3. All right. So that means our domain is x such that x cannot equal the original 0 we found, which was 5 halves, and this second 0 we found, which was 14 over 3. So there you go. Hmm. That's the first half of this question, and I'm not liking how it's kind of written out here. So let's put f composed of g of x equals, it's 1 over 13, 3x plus 14. Trying to cram this all into this space here. There we go. I think that's a better way to write this. All right, so now we need to do the reverse. We're going to do g composed of f of x. All right, so we're going to look at the f function first. And what makes that 0 on the denominator? It would be a 2. So x cannot equal 2. That's this part. So now we're going to take that whole nasty business and we will put it inside of g. So everywhere we see x, we're going to put this whole f function. So we have 2x minus 1 over x minus 2 plus 4 all over 2 times the quantity 2x minus 1 over x minus 2 minus 5. Now again, don't like working with these silly fractions. So I'm just going to multiply the top and the bottom by the x minus 2, which is the denominator of the two fractions. And that's going to give me 2x minus 1 plus 4 times the quantity x minus 2 on the top. And then 2 times x, 2x minus 1 minus 5 times the quantity x minus 2. There we go. Now we're going to distribute all this junk out. Slide over here a little bit and try and zoom out to keep everything in there as much as possible. So 2x minus 1 plus 4x minus 8, I believe is what we get there. And on the bottom, we're going to get 4x minus 2 minus 5x plus 10. Yep, plus 10. All right, forgot my parenthesis here. All right, combining like terms. On the top, we are going to get 6x, because these two combine to 6x, and negative 1 and negative 8. That combines to negative 9. And on the bottom, we combine the 4x and minus 5x. That gives us a negative 1x. And negative 2 plus 8. Yeah. And I'm going to factor out this negative on the bottom because I don't like having negative value on the bottom. So I'm going to send it to the top, which would just basically reverse all of these signs. There we go. Now we cannot have the denominator of that be 0, so 8 is another value. So I'm just going to rewrite this all over here. G composed of f of x equals this business, which was negative 6x plus 9 over x minus 8. I got a little long on my division bar here. All right. And our domain is going to be x such that x cannot equal that original 2, and then the 8 that comes from this denominator over here, x can't equal 8. So that is where our domain is not defined. With a square box around that guy. There you go. On to this section where we find the sine, cosine, and tangent for each angle. Back to some trig here. So we'll just write this sine equals cosine equals tangent equals, and we'll just copy and paste this all around to everywhere because it's going to be kind of the same chart for all of them. So save a little time. I really was trying to save time. Would have done this prior to me recording the video, but anyway, live and learn. So at 5 pi over 6, this is in quadrant 2. We sketch a little graph here. See 5 pi over 6 is here. It's a 30-degree reference angle. All these questions are unit circle questions. They're all on the unit circle in one way or another. So sine is 1/2 at this point, and cosine is square root of 3 over 2, and tangent is root 3 over 3. Or we could say 1 over root 3, but we don't like radicals in the denominator, so we really write it as root 3 over 3. Move on to b here, and b is negative root 3 over 2, and this is 1/2, and this would be root 3 for tangent. Negative 2/3, that's going to be in quadrant 3. So root 3 is positive. I was stopped there for a second. I was trying to make sure the tangent would be positive or negative, and cosine is going to be negative because we're also in quadrant 3. Maybe I better write this down. Quadrant 3 for this guy. This one was in quadrant 2. So now we'll move on to C. I'm just writing those so I remember which ones are positive and which ones are negative. So 13 pi over 4, well, that's bigger. It's gone a complete revolution plus some, right? So we subtract that 8 pi, which would be one total revolution. We come up with 5 pi over 4. That puts us in quadrant 3. So at 5 pi over 4, we have sine and cosine are both negative, and tangent will be positive. So we have negative root 2 over 2 and negative root 2 over 2, and tangent is 1. D, it looks like it's not in the unit circle because we have this weird 14 on the bottom, but if we subtract a full revolution, which would be 28, we end up with negative 7 pi over 14, which gives us negative pi over 2. Well, sine is negative 1, cosine is 0, and tangent is undefined because it is lying on the y-axis. So there's the square for that guy, square for that guy. You get a square, you get a square. It's Oprah squares everywhere. Awesome. All right, there you go. But actually, wait a second. Let me take these squares away. Oprah taking back her stuff. I forgot a critical piece here, so I'm going to move all this over to make your answers technically correct. I guess I could have grabbed the equal sign as well before. Could have done this both these columns. Doing this the fast, slow way, I guess. Let's get both these columns together. Right here. Oop, not that part. Just the equals. All right, slide that over. So you do need to include the angle. Whenever you write sine and cosine, you should include the angle. So this was 5 pi over 6 for this problem. So cosine 5 pi over 6, tan pi over 6. Sine pi over 6, of course. Sine 13 pi over 4. This is cosine 13 pi over 4. Tan 13 pi over 4. This is really redundant, I know, but if you don't include the angle, technically you could, I didn't quite get this one all right over here, clean this up. If you don't include this with sine, cosine, tangent, if you don't include the angle, you could technically get marked wrong. I'm having serious troubles over here with the sine of negative 2 pi over 3. All right, the rest of this should go better. And then d is sine negative 35 pi over 14, cosine negative 35 pi over 14, and tangent negative 35 pi over 14. Now, less Oprah-esque, I'm just going to put a box around both of these columns here. There's that half and some weird box for this one. There we go. Now we got it right. Okay, determine whether each function is one-to-one on its entire domain. If it is, find its inverse. All right, well, let's do a quick sketch of this function. See if I can get some straight lines out of this thing today. Oops, didn't want to erase that one. Yay, straight line. Let's make it a little longer, make it more straight. All right, good enough. Well, x cannot equal 2, so we'll have a, negative 2. We'll have a vertical asymptote at negative 2. These are both to the power of 1, so we have a ratio of our leading coefficients. So 3 over 1 is 3, so our horizontal asymptote is y equals 3. So we're going to make a horizontal asymptote here. All right. Didn't really ask us to graph this, but this is basically what our graph would look like. Now, our graph, I'm just going to find my point here, make sure I'm as accurate as possible. 1, 1 is really a point here. I guess I could find the intercepts and make this even more accurate, but I just want to make sure that this is the direction of everything that I have going on here. So anyway, that's where the lines are going to be graphed for this function. The function is one-to-one because it passes both the horizontal and vertical line tests. If you draw a vertical line, you will only get one value. If you draw a horizontal line, you will only get one value. It'll only intersect the function at one point on each of those lines for either horizontal or vertical line tests. So since it is one-to-one, we need to find its inverse. So basically, we switch all the x's and y's in the original function. So we have 3y over y plus 2 equals x. Now, we're going to do the fun job of solving for y. So we're going to multiply both sides by y plus 2. And then we're going to distribute this section over here. And then we're going to move this 3y over. Get 0 equals negative 3y plus y plus x plus 2. Sometimes when I'm talking, I do math badly. Something doesn't look right here. And that would be this thing here. It's plus yx plus 2x. There we go. All right, so I'm going to subtract 2x. Remember, I'm trying to get y by itself somehow. And then I can factor out a y here. Yeah, factoring out a y would be good. So negative 2x equals y times the quantity negative 3 plus x. Now I can divide both sides by that quantity. So negative 2x divided by negative 3 plus x equals y. These cancel out. So I end up with the f inverse function, or my inverse function. Excuse me. I ate some peanuts today. Anyway, let's make this look a little nicer. negative 2xy over negative 3 plus x. The answer that the instructor gave us was this. So he left the negative quantity on the top, but swapped around the x and this. So anyway, this is another way to write basically the same thing that I said before. But we want to put f inverse of x here is equal to this bit right there. All right. So on the denominator, I just switched those two values around, basically. So it didn't cancel out that negative. Anyway, this next one is a parabola that opens up. Well, this one fails our horizontal line test, as we would get two values drawing that line. So this one fails the horizontal line test. Therefore, it is not one-to-one. And it's not one-to-one because, like I said, fails horizontal line test. So we don't have to find the inverse of this function because there isn't one. And there you go for that guy. All right, evaluate each expression, more unit circle stuff. So here we are looking at negative root 3 over 2. Well, this is going to be in quadrant 4. I'm sorry, quadrant 2. What am I thinking? Cosine root 3 over 2 in Q2 is equal to 5 pi over 6. And cosine is only defined in quadrant 1 and 2, so that was the choice that we had to make. Arc sine of negative root 2 over 2, well, this is going to be in Q4 because sine is only defined in Q1 and Q4. So we have negative pi over 4. And tangent of negative pi over 4 is negative 1. So that is that little guy. All right, C is a little bit more complicated because negative 3/5 is not necessarily directly on the unit circle as we memorize all the things that are on there. So we'll just draw this one out. Tangent, TOA, is opposite over adjacent. So we'll just write those in here, negative 3 over 5. And we'll just use our Pythagorean theorem to find out what our hypotenuse is. So 5 squared plus negative 3 squared is equal to c squared. So 25 plus 9 is equal to c squared. That's going to give us 34 is equal to c squared. And root 34 is equal to c. That doesn't simplify, so we have root 34. Now we want secant, which is 1 over cosine or something. So we're going to have root 34 over 5, but tangent, or sorry, this is going to be negative in quadrant 4. So there you go on that guy. Secant is negative in quadrant 4. So there you go. Nice little box for that guy. What happened to my 5? There we go. Okay, logarithms. Oh my gosh, this is still all review pre-calculus stuff. We'll get into calculus soon, I hope. Anyway, so from pre-calculus, we should recall that log a m times n is also the same as log a m plus log a n. I'm writing this all down because I'm not the greatest at logs, so I encourage you to do the same kind of stuff because it gets you in the practice. So motor memory, writing this down will help you remember. But log a of m divided by n is also the same as log a m minus log sub a n. And then our third thing that we should remember is log a sub a m to the r is equal to r log, whoa, I think the shape is going out of control, log sub a m. Now, once we remember all of these properties of logs, that will help us solve these next couple problems. Actually, the next 4 problems. But anyway, so first thing we need to do is recognize that root 5 can be rewritten not based on a log property, just based on the property of square roots, to be 1/5, or the 1/5 power of what's inside the root. So once we do that, then we can use this log property where we can bring the 1/5 out front. So we have 1/5, and then we are going to expand what's inside, and we're going to use this second property that I wrote up here. Actually, I'll write this out first. So you can see this step of bringing that exponent to the front. So using that third property. Now I'm going to use the second property because I have an m over n, or a value over another value, rather. So we'll rewrite this as 1/5 ln, and we'll do the top one first because it's important of the order. So we have the quantity 4x squared minus 1 minus ln times the quantity 4x squared plus 1. And that is the answer for this problem. So put a little box here. We'll do one more doing it this direction where we are separating them, or expanding them rather. So we have a multiplication function on the inside here. So that's the same as that first property I told you or showed you earlier. So ln times ln the quantity x squared plus 1 plus ln x minus 1. So there you go on those two of expanding. Okay, for these next two, we're going to do the reverse of what we just did, and we're going to combine. So I'm just going to rewrite these really quick because I'm going to refer to them. So log sub a m times m is equal to log sub a, should have been sub a, m plus log sub a n. Get our a's in there. Ink to shape is killing me. All right, log sub a m divided by n is equal to log sub a m minus log sub a n. And then our third property, which was log sub a m raised to the r, is equal to r log sub a m. All right, so with all of these properties here, we should be able to solve the rest of our functions here. So let's deal with this one right here in the middle. We can move this back over here based on our third property here, based on this guy. So we'll have ln of 4 minus x squared raised to the 1/3 power. Now, since it's raised to the 1/3, it's a fraction. We know that this can also be written as ln root 3 of 4 minus x squared. So that's how I think I'm going to prefer to write this. And of course, we would bring down the rest of this junk with it, ln 3 plus that business, and then that business minus ln x. All right, so let's do order of operations. We're moving from the left to the right since all we have left are pluses and negatives. So we're going to use this first property, ln 3 times the root 3 4 minus x squared. And then our next function is a negative, so we're going to use this second property, and we're going to put that underneath, and it's just an x, so we have x. So that's the answer to this guy. Pretty simple. Now let's look at just the stuff on the inside of this quantity for this problem. We'll start there. We have a minus here, so we're going to put a fraction bar. We'll have x on the front, and then We're going to use two properties at the same time here. Hold on to your seats. X squared plus 2 squared. I moved that 2 using that third property to be the exponent, and then I just wrote that on the bottom. So I'll put this inside the bracket again, just so we can, actually we don't really need to, but oh well, I'll do it anyway. So 3 times that, and then we'll bring down this business, the plus ln 5 squared. Actually, so now we have 3. I don't need those brackets because that'll make it confusing. But anyway, so ln, and then we have this quantity here, and I'm going to use that third property again. I'm going to move that 3 up here to be an exponent. Since it's not a fraction, it can't turn this into a root. And then we have plus ln 5 squared. Now we can change this to multiplication because it's a plus, so that's using that first identity, ln, and then we have x cubed over x squared plus 1, and that's to the 6th here. I'm just distributing that cubed to be the inside here. And then times 5 squared. Actually, that 2 should have been on the outside. It doesn't matter. Either way, you get the same answer. So I'll rewrite this guy. So we have x cubed over x squared plus 1 to the 6th. Craziness. And then this is 25 because 5 times 5 is 25. Then, since that's the multiplication, I can just combine that a little bit more. So I have ln of 25 over 1 times that, so we'd end up with 25x to the third, or x cubed, and then x squared plus 1 to the 6th. So there's that guy. All right, so now we're going to solve each equation for x. All right, so we'll move that radical over, and that would square the 2. So we have ln x plus 1 equals 4. 2 squared is 4. So then we can take that ln and make it an e. So e does the swoop. So we have x plus 1 equals e to the 4th, and x equals e to the 4th minus 1. So there's the first one. And now we'll go on to the second one. We have a plus here, so we're going to combine this as a multiplication problem. So ln x times the quantity x minus 3 equals 0. We do that little swoop thing with this. That turns this into e to the 0, which is 1. So we have x times the quantity x minus 3 equals e to the 0. Now, anything raised to the 0 power is 1, remember? So this is really a 1 over here. So x squared minus 3x, distributing that x, and then I'll move that 1 over, so that's minus 1 equals 0. Erase this because that looks confusing. It looks like that whole thing is equal to 1, but it's not. Anyway, so there you go. Now we are going to have to use this this old formula here, because this x squared minus 3x minus 1 doesn't factor. So we're going to have to use the old standby here. Now our b is the negative 3, and the c is a negative 1, and our a is 1. So we're just going to sub in these values to this formula. Quadratic formula, or what do we call this formula? I can't remember. But anyway, it's a formula everyone needs to have memorized, that's for sure. It's the get out of jail free card, kind of. So subbing all of this in, and 2, and this is times 1, so that's going to end up being 2. Anyway, we reduce this all down. So we have 3 plus or minus the square root of negative 3 squared is 9, minus 4, but it's going to be a plus 4 because 4 times 1 is 4, times a -1 is a -4, and then the two negatives turn it into a positive, blah, blah, blah. And on the bottom, we got 2. So we have 3 plus or minus square root of 13 over 2. Still not done here. You need to recall that an ln or log functions can't have negative input values. If you have a negative input values, it just doesn't work. So knowing that the root 13 is going to be, if we use the negative portion of that, that's going to make the top negative. That's going to make the whole thing negative. So we only consider the plus version of this formula. So it's kind of a little tricky on this one, but you just have to remember that logs can't have negative inputs. So you have to evaluate whether you're going to get a negative input out of that. So there you go. All right. Hour and 15-ish minutes in, and we're finally to something that resembles calculus. No, we're not. Oh my god, I forgot E of the last one. So E will turn this to ln. We'll bring that x plus 3 out to the front. And then that gives us x to the ln of pi on the other side. I just put this in the front, the E here, and I put the x to the front here, and I had to get this ln in the middle. Sorry, kind of doing this one fast. So that means I can subtract 3 from both sides. So I get x equals x ln pi minus 3. So I still haven't isolated my x yet. So I can subtract this x ln of pi, and I get this. So now I can factor out an x. Yeah, that's going to end up being ln pi 1 minus ln pi. Yeah, there we go. Equals -3, and so now I can divide that negative, or both sides, by the 1 minus ln of pi. So I have x equals -3 over 1 minus ln pi. So letter C for this guy is equal to negative, and I'll put negative ln pi plus 1. Let's see, and then negatives cancel, or should cancel. Yeah, sucking out that negative on the bottom. And now I can cancel it. There we go. So now I have ln pi minus 1. All right, there you go. Okay, now we can do something closely resembling calculus. Actually, it's not closely, it just is calculus. And we are an hour and 18 in. So we're just going to use this graph and find out if this limit exists. And then if it doesn't, we'll explain why it doesn't. So we're going to look for x as it approaches 4, and we see that we have an open circle. Well, this limit actually does exist, even though there's a hole there, because we're looking at values from each side of 4. As we get infinitely close to 4, we still get values. It's only at 4 that we don't get a value. So as far as limits are concerned, the limit of x approaches 4 of f of x is equal to 1 because you return a value near 1. If I put in 3.99999999999 forever, you will get something that is almost 1. And same thing from the other side, x equals 4.00000, name the number of zeros and then put a 1. You will be almost at 1. So this is the answer to A. Now, if we look at f of 4, now we are specifically stating at 4, does this exist? And the answer is no, it does not exist, or it's undefined, because there is a hole specifically at that location. We aren't evaluating numbers from the left or the right as a limit function would. We are just looking at specifically the function of 4. We really need to understand that those are two separate questions and obviously have two separate answers. So this is undefined because of the hole at f of 4 and f of x. All right, so moving on to C, we have the limit of x as approaches 3 of f of x. So 3, we have a vertical asymptote. So for this one, again, it does not exist because we have an unbound relation here at 3, the vertical asymptote. So as we approach 3 from the left and as we approach 3 from the right, we are getting values that are closer and closer and closer and closer and closer to 3, but we'll never get to 3. But they go vertically forever. So unbound relation on that guy. So now we look at D and we look at f as approaches 2 and we get 2. For E, as x approaches -1 from the negative side only, we are at 2, as we can see here. We're only looking at this portion. So we have returned the answer of 2. For F, we are looking at the same problem, except we're only looking for things that are coming from the positive side. So it's still at -1, but from the positive side. So in that direction, we have -2 as our answer. Now, again, remembering when we look at a function as itself, we're not looking at it as a limit, we're looking specifically at 1 and what is the value at -1, rather, for this one. Sorry, I didn't mean to move this around. We return a value of the closed circle, which is at 2, not the open circle. However, when we reevaluate this as a limit of just -1, not isolating it as 1 from the left or 1 from the right, giving that upper negative and positive sign, we have two different values. So this does not exist because the limit of x as it approaches -1 from the left, or as we write it as x approaches -1 with this little negative up here, that limit does not equal the limit of x as it approaches -1 from the right, or the little positive symbol that I put up here at the top. So there you go. That's that guy. All right, and now we have the limit of x as approaches -4. So we look here at -4, and we have this oscillating business. So this does not exist due to oscillation as x approaches -4. We can put in a bunch of different values. We're always going to get the same value, except if we chose another slightly different number within that range, we're just going to get the same value over and over and over again. So it's oscillating, so it doesn't exist. So there you go. It's a little bit confusing, but let me rewrite this a little bit. Due to oscillation as x approaches -4. So we'll put that in the box. There you go. Okay, find each limit if it exists. If a limit does not exist, explain why it fails to exist. Lots of existing here. All right, so we can just do direct substitution on this one. So we'll just take limit of a as it approaches 5. So we're going to substitute that 5 in for a. We have 7 times the absolute value of 1 minus 5, and that equals 28. All right, that one was pretty easy. Now we try direct substitution on this one. Always try and direct substitution first. If we substitute it in on the top, we are going to get 0, and on the bottom, we'll get 0. Uh-oh, now we have a problem. So when we directly substitute this, we get 0 over 0. So now we have to do something else to try and evaluate the limit of x as it approaches 3 of this function. So I'm just going to rewrite it down here. I have x squared minus 9 over x minus 3. And then I'm going to rewrite my limit of x as it approaches 3. And the top I can break apart, kind of. It's a difference of squares. So we have x plus 3 times the quantity x minus 3 over x minus 3. Now, lo and behold, bamski, we're able to cancel these guys out. That was our problem, this 0 on the bottom. So I can rewrite this as the limit of x as it approaches 3 of x plus 3. Now I can do direct substitution, so I can stop writing that limit business, and we get 3 plus 3 is 6. So the next one is a little bit more difficult. We can obviously see that the 0 substitution situation here is going to give us 0 over 0. Just knowing that we get a 0 on the bottom tells us we need to do something else because we can't have that. So we'll rewrite it. Limit of x as it approaches 0, the root of 4 plus x minus 2 over x. Now I'm going to multiply this by the conjugate of the numerator and see if that helps me out in any way. Now when I multiply this by the conjugate, I'm going to get the limit of x as it approaches 0. I'm going to get 4 plus x, because it gets rid of that root sign, and then minus 4. And then that's going to be over. And I'm not going to distribute this x. Really important not to do that, because the x is the problem and I want to get rid of it somehow. So I can see these are going to cancel out. I ended up with just x on the top. And let's see. I'm just going to rewrite this down over here. Limit as x as it approaches 0. And that is x over x times this quantity of root 4 plus x, and then that root plus 2. And then plus 2 is outside that. Now I know I can cancel these x's, so I end up with the limit of x as it approaches 0 of 1 over 4x under the radical, or 4 plus x, sorry, plus 2. Now I can directly substitute this 0 in now. I'm not going to get 0 on the bottom. I need to put x here. Okay, now I can substitute in. And once I start substituting, I can stop writing this limit x as it approaches 0 business. So we got 4, the plus 0 under that radical. That's going to be 4, so that's going to be 2. So 2 plus 2 is 4. So I basically get 1/4 for this problem. All right, so this one's yet even more complicated because we have a fraction on the top, and I don't know about you, but I don't like dealing with fractions. But if I directly substitute, I see I get 0 over 0, so that's not going to work. It's going to take more space, so I'm going to just rewrite this over here. Limit of n as it approaches 0. And then I have 1 over the root of 1 plus n, that quantity minus 1. And all of that over n. I'm going to multiply this by the 1 plus n first under the radical. I'm going to try and get rid of this fraction on the top and make it a little bit easier. Easier for me, maybe not for some other people, but easier for me. Limit of x as it approaches 0. Actually, that should be n as it approaches 0. My bad. Anyway, this is going to be 1 minus the root of 1 plus n over n root 1 plus n. And as suspected, I'm going to run out of room, so we'll just recopy all this business over here. I wrote the x as it approaches 0 again. It should be n as it approaches 0, but I think you get the idea. Probably going to keep doing that through this whole problem. Anyway, I'm going to multiply this by the conjugate of the numerator. So 1 minus the root of 1 plus n. Its conjugate would just be changing that minus to a plus. So I'm going to multiply by that and see if that helps me at all. So I rewrite this as limit x as it approaches 0. And then I'm going to have 1, and then I'll have plus the square root of 1 plus n, and then minus the square root of 1 plus n, and then minus the quantity. Make sure you do this as a quantity because you're going to have to distribute that negative. And then on the bottom, I'll end up with n plus, or times root 1 plus n times the quantity 1 plus the root of 1 plus n. So I can see these two are going to cancel out. So I end up with the limit of x as it approaches 0. And then this is 1 minus n over n root 1 plus n times the quantity 1 plus root 1 plus n. Cool. This is all a mouthful. All right, so the top here I get 1 minus 1. Well, that cancels out. And then I get these n's finally cancel out. Yay, that's what I wanted to do. So I end up with 1 at the top, but it's a negative 1. Remember, I didn't cancel out this little negative here. We should just move all this down over here and rewrite it so we see what we got. The limit of x as it approaches 0 is equal to 1 over the root of 1 plus n times the quantity 1 plus root 1 plus n. And now I can finally directly substitute, so I can stop writing the limit business. So I'm going to substitute in that 0, the root into the, for n, not x. I know I keep writing x, but you get the idea here. 1 over, well, all this business on the bottom is going to end up being 2. So we end up with 1 half. And I should have written this as negative up here, so I remembered. I told you guys to remember, and then I forgot it. So this negative carries through as well. So we end up with negative 1 half as our answer for this guy. A lot of work to show, but there you go. Now you have it. All right, for E, this one, we'll try direct substitution first. So we have 4 times the quantity pi over 4 over, and then tangent, and then that's pi over 4. Well, we have 4 pi over 4 over tangent, and tangent is root 2 over 2 all over root 2 over 2, which tangent at pi over 4 is really 1. And on the top, we end up with pi, so we end up with just having 1 for our answer. All right, the limit of x that approaches 4 into this business. Well, if we plug in 4 directly, or direct substitution, we end up with 0 over 0. No good. So now, I know this is like that stair step looking thing, I think. So let's evaluate x that approaches 4 from the plus side. Well, I'm going to get a positive on the top. And if we evaluate it from the negative side, we are going to get a different value. So basically, this does not exist because, or as the limit of 4, as the limit of x as it approaches 4 from the left, or 4 negative, does not equal the limit of x that approaches 4 from the right of that. So this is why it doesn't exist. Now we have a piecewise function situation where we want to evaluate. So we're going to plug in the -2 into the bottom one here, even though it says only less than -2. We're going to find out what that value is, and it should equal the same value as what we'd get from the top one. And just working this out, get down to, we get a 2. Now let's plug in to the top formula. So we have negative of -2 squared minus 2 times -2 plus 6. This is going to be -4 plus 8 plus 6. Together is going to be 14. Wait, what did I do here? This should be -2. I wrote the plus 6 for the bottom function. That's a problem. All right, so anyway, we end up with 2 for this as well, so our answer is 2. All right, for this next group, given that the limit of x as it approaches c, f of x equals -6, and the limit of x as it approaches c, g of x equals -2/3, use the properties of the limits to explain, use the limits to evaluate each of the following. If a limit doesn't exist, explain why. All right, so we have f of x equals -6 and g of x equals -2/3. All right, and we want to do the limit as x approaches c to this business. Those are our values we're going to plug in for f of x and g of x, basically. So I'm just going to, I kind of shortcut this. I don't know if this is the best way to do it, but I just substitute those values directly in for f of x and g of x. So the limit of x as it approaches, or actually, yeah, I don't even need to write that because I'm doing the substitution. So I have 1/2 times -6 minus 3, and then that is times the -2/3. And that is going to be equal to, so -6/2 is going to be -3, and then -6/3, that's going to be +2, so we get -1 for this first one. For this next one, we are going to basically do the same thing. I think this is technically how you're supposed to write this, so I do 1/9 the limit of x as it approaches c of f of x plus the limit of x as it approaches c of g of x. Then you substitute in those values. Basically, on the previous one, I just kind of skipped rewriting the whole expression out this way. But so we get 1/1/9 times -6 plus -2/3. Yep. So we have -6/9, which is going to be -2/3. Uh-oh. We got -2/3 plus -2/3. This makes this much easier to deal with. We don't have to find common denominators and all that business. So a -2 plus a -2 is -4. So I get 1/4. We do the inverse multiplication to deal with this business, and we end up with a -3/4. So that's that business. And so number C, we only have g of x, and that's squared. So I'm just going to do that direct substitution thing. I'm just going to put in the -2/3. I'm going to square that business, and that turns out to be 4/9. And that is that guy done. Quick and easy. All right, so if 3x is less than or equal to the function f of x is less than or equal to x cubed plus 2 for 0 less than or equal to x less than or equal to 2, then use the squeeze theorem to find the limit of x that approaches 1 of f of x. So I'm just going to rewrite this with the limit of x as it approaches 1 for this whole thing. So limit of x as it approaches 1, 3x is less than or equal to limit of x as it approaches 1, f of x is less than or equal to limit of x as it approaches 1, x cubed plus 2. Oh my gosh. All right, so we can just directly substitute our 1 in here. So 3 times 1 is less than or equal to f of x, which is less than or equal to the 1 cubed plus 2. Well, 3 times 1 is 3, is less than or equal to f of x, which is less than or equal to 3. So, by the squeeze theorem, we have proved that this is 3. Rewrite this. 3 by the squeeze. Oh, I put die. The squeeze theorem can die. Anyway, you see my point. All right, it's getting late for me. All right, so determine the open intervals on which the function is continuous, list any discontinuities, and classify them as removable or non-removable. So first, we have f of x equals, and then we'll factor the top part here to be 3x plus 2, x minus 1. And then we have x minus 1 on the bottom still, but that's going to cancel with this top, so we know that we have a hole at x plus 1. So x cannot equal 1 because there's going to be a hole there. But if we put in 1, we need to find out where that hole is vertically. So on the y-axis, we need to find the other half of that ordered pair, rather. So 3 times 1 plus 2 is equal to 5. So that means our ordered pair is 1 comma 5, and that's where our open circle is going to be. Now the rest of this is just simply a line. If we set this remaining piece to equal to 0, we will find our other our 0 really on the x-axis, which is x equals -2, so that, or -2/3, which is somewhere here. So here's our graph, and you don't necessarily need the graph to answer this question, but it's kind of helpful to see the graph. And you can see this function is continuous, along the entire line, except, so the function is continuous except, my ink to shape is not helping me right now, except for a removable discontinuity at x equals 1. Now remember, the problem asked for us to determine the open intervals on which the function is continuous and to list any discontinuities and classify them as removable or non-removable. So this is our complete answer. All right, for this next one, we have a piecewise function. So I immediately question whether this is going to be a jump continuity, which is non-removable. But let's test it out. We'll take this 2 and we'll plug it into the top part of the function here, and we get 5 minus 2 equals 3. And so that gives us an ordered pair of 2, 3, and it's included because it's x is less than or equal to 2. Now since it's less than, I can plug in 1, and I'm going to get 5 minus 1 is equal to 4. Little mistake there, but anyway. So I have an ordered pair of 1 comma 4. So now this kind of gives me the slope of this line. It's basically a slope of 1, or -1 rather. So there you go. That is the first part. Now let's look at the second part. Now I know it doesn't say equals to or greater than or equal to, but we'll plug in 2 anyway. So we get 2 times 2 minus 3, and that equals 1. So I'm going to get an ordered pair of 2, 1. Now I'm going to put an open circle at 2, 1 because it is not included. It doesn't have a greater than or equal to, it just has greater than. So that means it has an open circle. Now I can only enter x's greater than 1. And again, my slope is 1, or negative 1 rather. So you can see we do in fact have a jump continuity, and jump continuities are not removable. So the function is continuous except for a non-removable discontinuity at x equals 2. And now that I'm kind of looking back at this, I drew the graph a little incorrectly. My green arrow should actually be pointing up, because if we put in 3, we're going to get 6 minus 3, and that would be 3. So at 3, it would go up to 6. So anyway, I think you get the point. I'm not going to re-sketch it and erase stuff, but there you go. That's still the answer. We get the same answer. So let's just hope I do better on C's graph here. So we know in this case x cannot be 0. And actually, x needs to be greater than 0 because we can't have a negative in here, otherwise we're going to get a imaginary number. So we can't have negative x because it gives imaginary numbers. And we can't have it be 0 because it'll make the inside undefined. So we can only use things that are bigger than 0. So what would this look like if we set it to equals 0? We'd have x equals negative 1. So we can plot or make a little number line here, and we can put a negative 1 here, and we'll put a 0 here. And we're just going to choose some points that are in between or on the opposite sides of these intervals. So I'm going to use negative 2, negative 1/2, and 1. Now I'm going to test each one of these. And so negative 2 plus 1 over negative 2, well, I'm going to get a negative over a negative, so that's going to be positive. So this region, negative 1 to negative infinity, is all going to be positive. I'll put in negative 1/2 plus 1 over negative 1/2. Well, that's going to give me a positive number on the top and a negative number on the bottom, so I'm going to get negative. So in the region between negative 1 to 1, I'm going to get a negative number. We'll put in 1, and we can see that we get positive, positive, so that's positive. So here's what we have. This function is only going to be defined in the areas that are from negative 1 to negative infinity and from 0 to infinity. And the question is going to be, do we include that negative 1 and 0, or 1 or both of them? So here's our graph of this function. So I'm going to erase all this so I can write in my information here. And basically, we have a non-removable discontinuity, but it's on an interval. So I'm going to write there is a non-removable discontinuity on the interval of negative 1 to 0. Now, this is an important question here about whether we include the negative 1 or the 0 or vice versa. So we actually don't include the negative 1 when we're discussing the interval between by which it's not defined or when it's below 0, because at -1 we are actually defined. So we want to know when we're not defined. So we have -1 to 0, and then we include the 0 in where we're not defined. Express this a little bit further, we are defined on -infinity to -1, and then there's the gap, and then it's um, 0 to infinity. So it looks a little backwards, but when we're talking about the discontinuity section, we have to remember which we include and which we don't. All right, so on to D. Now, where would this have a discontinuity? Well, if we look at this as x plus 1 over 2 times the quantity of x plus 1, because we can factor out a 2 in the bottom, now we can see that we can cancel these two out, which means there's a hole at x minus 1. And the answer to this problem is 1/2. So y equals 1/2. So let's draw this line, or this graph. Now, as I said, because we have the x plus 1 canceling out, there's a hole at x negative 1. So when x, oops, I'll just work out the problem for you really quick. X cannot equal, what am I doing here? Zing! Cannot equal a -1. Finish off my graph here. There's my hole. And since it's y equals 1/2, you can see that I'm in between the 0 and the 1. There is a or the function is continuous for all real numbers, or yeah, except for a removable discontinuity at x equals -1. Removable discontinuity at x equals -1. There you go. All right, E. We got a tangent function here, and that's kind of scary to a lot of people, but if we remember that tangent is defined at -pi/2 is less than tangent of theta, which is less than pi/2. So I'm just going to take this junk right here, the x, the 2x, and I'm going to put it in the middle here. So I have -pi/2 is less than 2x, which is less than pi/2. Now, if I divide everything by 2, I'm going to get -pi/4 is less than x, which is less than pi/4. So dividing by 2, I flip the inverse and multiply, so I ended up with 4 on the bottoms there. So normally, get my line straight here. Normally pi is, we basically got a shrink of our width of our tangent function here. Usually it goes from pi/2 to -pi/2 to pi/2, but we just proved that our interval is really between -pi/4 and pi/triangle. I'll fix that here in a second. It should be pi/4. But it still looks like a tangent line. And there we go. So where are our discontinuities? Well, our discontinuities are due to this unbound behavior at these vertical asymptotes. So there are non-removable discontinuities because they just are going forever um, to infinity and beyond. So there are non-removable discontinuities every, let's see, um, pi over 4. Well, every pi over 2. So at x equals pi over 4, and then plus k pi over 2, because you can see that, the distance between them is pi over 2, actually, where k is a set of integers. So I think I'm writing this the right way. An integer symbol is this cool looking z. So there you go. All right, so the last one for this section is an ln function. And as we know, ln functions can't be negative, but we've kind of taken care of that in this situation because we are only going to deal with the absolute value um, of these numbers. So we can really put in negative numbers for x. So, like I said, log functions cannot be negative. So our domain should be 0 to infinity normally. But in this case, because we have the absolute value signs, our domain is really going to be negative infinity to infinity. But let's evaluate the x minus 3 at greater than 0. And we find that x cannot equal 3. So if it's 3 in there, we're going to get 0. So that means we have a horizontal asymptote at 3, where x equals 3. So f of x is continuous on the entire real line except at the non-removable discontinuity at x equals 3. Except at a non-removable discontinuity. I wish I could write as fast as I talk. At x equals 3 or 3. So that's the answer to this guy. I know I didn't graph it, but we can go ahead and graph it just for fun, and you can see why the domain actually would be negative infinity to infinity. But here we go. Normally, we would have an ln function that would start at close to 0 and would arc up to the side. But we've shifted over that vertical asymptote from 0 over to 3. But in this case, because we have that absolute sign, we can do negative numbers. All right, so here we kind of have the same question, except for we just want to know what the intervals are where it is continuous. So, and we recognize this graph from earlier problems. So f is continuous on the following intervals. Basically, we just have to say where we can have the graph instead of where we don't in the previous following problems. So the first interval that we can look at is negative infinity up to negative 4. Now you can see It also says assume -4 is not defined, so that's a clue. And then the next interval is -infinity to 1 included because we have a filled in hole, or filled in dot, rather. And then that's from the negative side. And then from the positive side, it's -1 because it's an open hole. And then we're going up to 3, not included because of the vertical asymptote. Then we go from 3 to the hole at 4. And then we go from 4 all the way to infinity. So there you go. You just kind of follow it left to right and write it out. All right, use the intermediate value theorem to show that f of x equals 2x to the third minus 3 has a 0 in interval 1, 2. All right, so this is basically a limit function here that we're going to kind of figure out. And we're basically going to try and prove that f of 1 is less than 0, which is less than f of 2. So we'll just plug in this. And I'm getting that from the interval 1 and 2. So we want to show that there's a 0 in between there somewhere. So we got to prove it? No, too many O's. How about we prove it? There we go. All right, good thing it's math, not English here. All right, so I can set up my two limit functions here. We'll start with the limit of limit as x approaches 1 of my function, which is 2x cubed minus 3. And then my other limit function, which is going to be limit of x as it approaches 2, the second number on my interval. And you can see that here. Actually, let me make these two separate colors. See if I can get, oops. See if I can get this whole, nope. Nope. One more try here. There we go. Change that to green. All right, so 2x cubed minus 3. So we have limit x as it approaches 1 and limit as x approaches 2, which is the interval that was given to us. So we can do this by direct substitution pretty easily. X times 1 cubed minus 3, well, that's going to just give us 1, -1, which is definitely less than 1. And then we can direct substitute here as well. So we have 2, times 2 to the third minus 3, and that equals, so 2 times 2 is 4, times 2 is 8, times 2 again is 16. Double checking my math in my head here, but yep, that's 16. And then 16 minus 3 is going to be 13. And that is an awfully big number compared to 0. But yeah, it is definitely bigger than 2 for sure. So, looking at these two limits, we can make this statement, therefore, by the intermediate value theorem. And we might want to check with your instructor how he wants you to state this, but I'm going maybe a little overkill here, but I'm being very thorough. By the intermediate value theorem, there must be a number c a number c in 1 comma 2 such that f of x equals 0. So I'm just saying there's something in between those two numbers that x will equal 0 at some point. So in shorter terms, you could say f of x has a root in the interval 1 comma 2. And a root being an interesting word, but we're planting seeds on the x-axis. All right, so now we need to find the vertical asymptotes, if any, of the function. So we can split this up into 4x over 2 minus x, 2 plus x. And that doesn't really help us too much because we can't cancel anything. But we can see that we have vertical asymptotes at x equals -2 and 2, because that's where we'll have our zeros. So there you go. First one pretty easy. Got one more where we're just finding vertical asymptotes here. And that is this guy, which is a little bit more complicated because, well, we have some trig in here. And since we do, I'm going to go over it a little more detail. And cosecant is somewhat related. Well, cosecant is 1 over sine, so it's related to sine. So I'm just going to take a slight step back here, and I'm going to draw a full cycle of sine. I don't necessarily see cosecant and secant right off the bat, so I always draw what they're related to, and then that helps me draw the inverse function. Well, it's not really the inverse function; it's just cosecant and secant. Anyway, you can see wherever we cross the x-axis, that gives us vertical asymptotes for our function of cosecant. So we have our graph here, and that would be one full cycle. Now, I purposely left off the labels on my x-axis there. We start at 0 and end at 2 pi for a normal cycle of sine. So we can see that 0 is less than or equal to pi over x, which is less than or equal to 2 pi. Now I'm getting that pi over the x in the middle from this function right over here. Now I basically divide both sides by pi, and I'm going to get pi is less than or equal to, less than or equal to x, which is less than or equal to 2. Because when I divide 2 pi by pi, excuse me, the pi's will cancel out. So I'm dividing this side by pi, the middle by pi, and this by pi. So now I can see that my period is 2. All right, so now I know that every asymptote is really separated by one full unit. So I'm going to go ahead and label these numbers here. So actually, I just labeled that incorrectly, didn't I? I basically said that this whole thing is 1, not 2. So hang on a second. Let me erase these guys really quick. Sorry about that. So this middle one is a 1, and this right here would be 1/2, and this right here would be 1.5 or 1 and 1/2, or 3 over 2, however you want to look at it. Anyway, so you can see that I'm getting these asymptotes every whole number, 1, 2, 3, 4, 5. So our vertical asymptote is equal to x equal to k, where k is a set of integers. So this fun little z. There you go. Okay, find the limit. Limit is x approaches 4, 4 minus x over 2. Then find delta less than 0 such that f of x minus L, absolute value, is less than 0.01 whenever 0 is less than x minus 4 less than delta. All right, so our limit of x as it approaches 4 of this function is equal to, we can just directly substitute our 4 in. So we end up with 4 minus 4 over 2, which is 4 minus 2, which is 2. All right, so now now that we know what our limit is, this is our L, this is our limit, and we know what our function is because it was given to us right here. That is our function of x. So we can plug this into our absolute value bit here. So we'll take our f of x, which is the quantity 4 minus x over 2, and then minus our limit, which we just found a moment ago by direct substitution, so minus 2. And this is all less than 0.01, which they gave to us already. This is the less than 0.01. I guess I could have circled this whole thing, but anyway, that's that part of it. So now we just need to do the algebra and sort this down and find out what our value is that we need to be less than to find our epsilon. So we combine like terms. We got 2 minus x over 2, the absolute value of that. So I just combine this negative 2 with this 4. It's not distribution because really we don't need those quantity signs because we're not multiplying or anything. So I factor out a half. So I get 4 minus x. And then I can put that half on the outside of the absolute value. And then I can multiply both sides by 1/2. And I end up getting 0.02. So, and I can rewrite this inside piece because it's absolute value. I can rewrite it as x minus 4 because it doesn't matter order of operations. We're always going to get a positive value. So our delta is equal to 0.02 or less. So that's the answer. I suppose you could write this answer as delta is less than or equal to 0.02. But in our solution guide for this, it was written this way, so I'll just box that one. Okay, so prove the limit of x as it approaches 2 of 3x minus 10 equals negative 4 using the epsilon delta definition of the limit. All right, remember just from the last problem, we had this setup of the absolute value of the function f of x minus limit is equal to epsilon. So this is our function. This is the limit. We don't have to do any substitution here because we've already found that it's already telling us what the limit is, minus 4. So we can do our analysis here. We can move that negative 4 to the other side, turns into a plus 4, so we can plug this all in. And we have our function plus our limit here. Because it was a negative, it turns into a positive on the other side. So just make sure you remember that part. So here we go. We're going to combine like terms like we did before. So we end up with 3x minus 6. The absolute value of that is equal to epsilon, or sorry, less than epsilon. I keep trying to say equal to, but it's less than. Very important. So I factor out the 3, put the 3 on the outside, less than epsilon. Then I get the absolute value of x minus 2 is less than epsilon over 3. All right, so we finally got to the end here of this part, but we need to write the proof of this. So the proof is kind of this little paragraph. Given epsilon is greater than 0, choose a delta equal to epsilon 3. So delta equals epsilon over 3. All right, and I got that from my analysis over here. So if 0 is less than the absolute value of 2, I'm sorry, x minus 2, and I got that from the other thing, is less than epsilon over 3. Now this is bothering me. This needs to have the other half of the absolute value sign there. Otherwise it just looks like 1x minus 2. Anyway, then, and I basically am just going to write my whole analysis here. I don't necessarily have to write every single step, but I have to at least get the beginning, middle, and end here. So here's the beginning, and I'll write a middle step here. And then I'll write the next step where I brought out the 3, and this is where I changed things up. I'm going to say this is less than, because that's what I'm trying to prove, is that it's less than. So 3 delta, actually 3 delta, which is equal to 3 times epsilon over 3, which is what I got from my answer, which is equal to epsilon. And that's what I wanted to get. So therefore, by the definition of a limit, by the definition of a limit x as it approaches 2, x approaches 2 of 3x minus 10 is equal to negative 4. And that's the proof. So I am going to say that this is the answer right here in the box. So there you go. Okay, find each limit. And our first one here is the limit of x as it approaches 1/2, but from the positive side of 1/2. So this one is D and E, as there's no way that we can factor this. We can't substitute direct in. There's no way for us to eliminate this 0 we're going to have on the bottom. So we have a vertical asymptote at 1/2, but which way does it go? Positive or negative? Well, we know this function actually is going to be, as we're coming to 1/2 from the positive side, it's going to be going positive. Now, why would I know that? Well, if we input something really close to 1/2, by really close, I mean really, really close. I mean really, 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 really close to 1/2 from the positive side. You're going to end up with a really large number, larger and larger and larger. Because whatever that value is that you put in for x on the denominator is going to just be the same value that's on the top. So it's just going to continue as you get closer and closer to that 1/2. Be multiplied by 2 and then subtracting 1, and it's just going to go up and up and up and up and up and up and up. So it's due to a constant value on the top. Nothing's changing with the value on the top in respects to, you put in 1/2, so 0.5000001. Well, you have 0.50001 on the top, but it's being divided by 2 times that minus 1. You're going to have this basically number that's really close to 0 there. So, or actually, sorry, really close to, let's see, what would it be? Yeah, it's actually going to be really close to 0. But anyway, therefore, as x approaches negative 1/2, the line will be moving in the positive infinite direction. That's really what I wanted to get at. So our answer is going to be positive infinity, or does not exist because of unbounded behavior. So there you go. All right, so for b, we have the limit as x approaches -1 from the negative side. So if we put in -1 into this function, directly substituting it in, we get 0 over 0. What a bummer. All right, so let's see if we can kind of factor this in some way. So we have x plus 1 over x minus 1 squared. And then we're going to have x squared plus 1. Can I just write it as x plus 1 squared? I think I can do that. So the limit of x as it approaches -1 from the minus side is equal to x plus 1 over x, and I'm going to factor out that perfect square over there, x minus 1, x plus 1, and then x plus 1 squared. Nope, I don't think you can put the squared to the outside here. This has to be on the inside. Yeah, that makes me feel better. Fix this one over here too. Squared plus 1. All right, so where were we? Okay, so now we can cancel out this x plus 1 with the x plus 1 on the top. So now we have the limit as x approaches 1 from the negative side, or from the left. And that's going to be equal to 1 over x minus 1 and x squared plus 1. All right, well now we can directly substitute in our -1. So we are going to have 1 over the -1 minus 1. It's going to be -2. And then the -1 squared plus 1. So, oops, subbing in now, I don't need that x. So -1 squared plus 1. And that's going to end up being 1, or sorry, 2. So we end up with 1 over -2 times 2. So this first quantity is -1 minus 1, so that's -2. And the second one is going to be 1 plus 1, so that'll be 2. So on the bottom, we end up with a -4, so 1 over -4. And then that's the answer. So put a box on that guy. Okay, let's look at limit of x of -1 from the left side, or the negative side. And plugging in -1 would make this 0 over 0. So let's look at this if we factor. And the top factors to x minus 1, x plus 1, and then of course we're over x plus 1. Actually, this is x minus 1 squared. So x minus 1, x minus 1. So nothing cancels. So that means this does not exist. But we need to know which direction. So it is from the negative side, it's going to be going to -infinity. So it's a -infinity. So this does not exist due to unbounded behavior at x equals -1. So we basically have a vertical asymptote there at -1. And that means we have unbounded behavior. All right, another evil one with some trigonometry functions in here. Ah! What do we do? Run away. We're on fire. Well, secant of x is equal to 1 over cosine of x. Or, well, I mean, let's think of this as secant is related to 1 over cosine. And being as I have difficulty, and cosine at 0 is 1 or 0 degrees. So I'm going to sketch the graph really quick here. And like I was just saying, I need to actually see cosine so I can see secant. So I'm going to just sketch a cosine here really quick. And I'm not going to sketch a whole one, but at least half of a cycle here. So kind of see what the secant line would look like. There's where cosine would be. And x equals 0, we can see cosine is 1. And then we can also see secant would also be somewhere around 1, because that's where it would start turning to go back up on the other side of the y-axis. But we have this kind of shrinkage situation here. So let's look at that part of it, since it's secant x over x. We can see this part, like I said, is going to be equal to 1. And now we have 1 over x. Well, we know what that looks like. We know that that graph is kind of this arc here in quadrant 1. So we kind of have this situation going here. So there's a vertical asymptote at 0 because, well, you can't put 0 in the denominator. So it kind of cut this secant section in half. So we can see that we're going to positive infinity and the plus side of 0. So this doesn't exist due to unbound behaviors, uh, just like the last one, just at a different place. So there you go. All right, so now we're looking at a limit function from the left side of 0. And we kind of basically just have an exponential function here. But in the exponent, we have something that's getting bigger and bigger and bigger. We have a constant on the top. We have an x value on the bottom. Our constant is -2. So we're going to get something that's just bigger and bigger and bigger and bigger and bigger and bigger and bigger. But on the negative side. So what is happening here is, since it's getting bigger and bigger, we have positive infinity is where this is kind of not defined. What are we saying here? Unbound behavior. This is the non-removable discontinuity in the graph. So there you go. That's letter E. All right, so this next group of problems is find the horizontal asymptotes of each function. Well, our exponent here and our exponent here, the numerator is greater than the denominator, so that tells me that the bottom is going to reach 0 first, so we'll have 0 on the bottom. It means there's no horizontal asymptote here, but there is an oblique asymptote, so we have to check for that. But this problem isn't asking for that, so it just says find the horizontal ones. Well, this one doesn't have any. So our answer technically is just none. That one's pretty easy. Now this guy looks super nasty, but we really just need to look at these exponents in the front, and 4 is equal to 4. So we use a ratio of the leading coefficient, which in this case is 3 over 2. So our horizontal asymptote is y equals 3 over 2. So right there at 1.5, we got a horizontal asymptote. All right, and so this one, the
numerator's exponent is less than the denominator's, meaning the numerator would get to 0 first, so we would actually have something here. But it means that we have the horizontal asymptote at y equals 0. So I do all those kind of from a memory type thing, which you heard me kind of saying the bottom will get to 0, the top will get to 0, first or whatever. So I kind of, even though that's maybe not technically correct, but that's just the way I remember it. So the alternative method to doing this, as we saw in class, is, as our instructor says, taking control of that denominator's exponent value of the x. So if we multiply by 1 over x squared, because the 3 has an x squared, we want to get that rid of that. We can see that we have 9 over x to the third minus 2 over x to the third in the numerator. Oh, sorry, 2 over x to the x squared. And then that just leaves us with 3 on the bottom. Well, 9 over x to the third is really getting close to 0. And 2 over x to the x squared is also getting closer and closer to 0. So we'll just assume or just plan on those being 0 for this case. So we end up with 0 over 3, and that's 0. So there. All right, so now we're getting into some real fun stuff. Find the equation of the tangent line of the graph of y equals square root of 2x plus 2 at x equals 4. Well, let's evaluate y equals square root of x, 2x plus 1 at 4. So we'll plug in the 4, and then we end up with 9 on the inside, so that's 3. So we're looking for the tangent line that goes through the point 4, 3. We're going to need that for later, so I've just kind of gotten that out of the way. Now, the slope of my line is equal to the slope of my tangent line is equal to the limit h as it approaches 0 of the function a plus h minus the function of a over h. So we can substitute a plus h and the a into our original function and create this limit here. I have square root of 2 times a plus h plus 1. And that minus the quantity with square, I guess the square root would really suffice for our negative here. Keeping the negative on the outside. But anyway, 2a plus 1 over h. I know I'm going to need a lot of room here, so I'm just going to take this work and move it off to the side here. Give me a little more space so I can get one more step in this row. So I'm going to multiply, excuse me, the numerator and the denominator by the conjugate of the numerator. So notice I wrote the same thing as the numerator except changed the negative to a plus. And I'm going to do that to both the top and the bottom. And the reason being is it's going to get rid of those radical signs on the top. So I can start dealing with this h and try and get rid of the h on the bottom that's causing this function to be 0. So on the top, I end up with 2a plus h plus 1 minus, now it's important that I have these quantity signs or the parentheses, 2a plus 1. And this, of course, all over h. Fortunately for us, this one's a little bit easier to distribute everything out. We don't have to deal with any squares or foiling or anything like that. Make sure I put the stuff I multiplied the bottom by on the bottom here. And there we go. All right, so now I have the limit of h as it approaches 0. And I'm just going to distribute the 2 and distribute the negative, so I get all of this all expanded out. So I have 2a plus 2h plus 1 minus 2a, and this is where I go negative 1 because I'm distributing that negative. That's why it's important to have those parentheses there. And then, of course, everything that I had on the bottom stays the same, so I bring that over. And what do I do next? Well, I cancel all crap on the top that I don't need anymore. And I basically am left with 2 over my radical bits. So I'm just going to go to directly substituting in my 0 here because I know that this is going to work now. So radical 2a plus 0, substituting that in for h, plus 1, and then plus the radical of 2a plus 1. Well, the radical 2a plus 0 plus 1 is really radical 2a plus 1. And this is going to give us our slope. So our m is equal to, let me move this over so I can write it out in front. M is equal to 2 over these two radicals that are being added together. Now remember, we had said in the beginning that this graph is going through at x. We want to know that tangent line. So we'll just use f of 4 into this new function that we've created. And that is going to give us 2 over the radical 2 times 4 plus 1 plus radical 2 times 4 plus 1. So we end up with 9 under both of these, so that's really 3 and 3. So we have 2 over 6, which then we end up with 1/3. Now, we're not quite done yet because that just found us the slope of the line. And this problem is asking for the equation of the tangent line. So we have y minus y sub 1 is equal to the slope times the quantity of x minus x sub 1. Well, remember I did that problem in the beginning to find the point? Here's where we're using it. The y minus the y value, y sub 1, which is 3, is equal to the 1/3, the slope we just found, times the quantity of x minus 4, which was the original point that we had. So now I'm just going to move this stuff around until I get my y equals mx plus b. So I need to distribute that 1/3, and I need to move over the 3. So I'm kind of going to do this all in one fail swoop here. This is going to be minus 4 over 3, and then plus 3. But the plus 3 is actually going to turn into 9 over 3. I'll just write the plus 3 here, and I need to change that to 9 over. Yeah, it'll be 9 over 3. So negative 4 plus 9 is 5. So I'll rewrite this up here. Y is equal to 1 over 3 x, or 1/3 x, plus 5 over 3, or 5/3. This is a long trail to our answer, but this is the final answer for this problem. So there you go. All right, for this problem, we need to find the instantaneous velocity of a particle with position function s of t equals 2t squared minus 3 at time t of 2. So this is a limit function. So v, velocity of a, is equal to the limit of h as it approaches 0, and f times quantity a plus h minus f of a over h. So we combine these functions together, or plug the function into this limit evaluation. I don't know how to really say that, but anyway, limit of h as it approaches 0 is 2, and then I'm putting in the a plus h where there's t's in that value, and then minus 3, and then minus f of a. So basically I'm just going to bring that function down into this limit, and I'm changing the t's to a's, much to my chagrin. And this is all over h. All right, so we can start expanding this out, and I am clearly not going to have enough space to expand this out. So let's start a new line here. Of course, bring down our limit notation, and I'm just going to start expanding here. So it would be 2, and then a plus h squared is going to come out to a squared plus 2ah plus h squared. And you're going to get pretty good at remembering that, because you're going to do this a lot. Minus 3 minus, and make sure you put this parenthesis here because you're going to have to distribute that negative, but we have a squared minus 3. And then all of this junk over h. All right, so now let's distribute. So we'll do limit of h as it approaches 0 of 2a squared plus 4ah plus 2h squared minus 3 minus 2a squared plus 3, because I'm distributing that negative, all over h. All right, now let's get cancel happy. This all cancels. This h is going to cancel there. So what we're left with, I'm going to start on a new line again. So the limit of h as it approaches 0, and I'll just write down what we have left on the top there, which is 4a plus 2h. Yeah, that's everything. Seemed like not very much, but anyway, now we can substitute in our 0, and we're going to be left with just 4a. Now what do we do with that? We enter in our time value, which was 2, into this function. So velocity of 2 equals 4 times 2, which is, and this was the 4a here, and that was the 2. So we just get 8. 8 is the solution to this problem. Okay, now we need to find the derivative of the function f of x equals 2 over x minus 1. So as we've already been using this, we have the limit of h as it approaches 0 of f times a quantity, well, not f times a quantity, but f function a plus h minus function of a over h. I'll move this over here just so I can have more room to do the problem. So now we need to put that a plus h into our original function wherever there's an x. So we have the limit of h as it approaches 0, 2 over a plus h plus 1. I'm sorry, minus 1. And then minus the original function, and then of course replacing that x with the a. So we have a minus 1. All of this over h. Now I'm going to multiply the top and the bottom by, I'm going to try and clear the fractions on the top by multiplying by the denominators of the top fractions. I'm going to do that to both the top and the bottom. This is going to make this much easier to manage. Now, since I do that, the first two will end up with the denominator of the previous two. So it'll be 2 times a minus 1. Sorry, All right, A minus 1, and that quantity. And then, of course, minus the other 2, and it's going to get the other quantity. So A plus H minus 1. And this is all over H times quantity A plus H minus 1 times the quantity A minus 1. All right, so we have all of that. And now I need to distribute all this stuff since there's no squareds and all that stuff. This will make it pretty easy. So we have 2a minus 1 minus 2a plus 2h. Hang on a second. I have not distributed correctly here. I'm going to distribute this negative. So it's going to be minus 2h and then plus 1. No, plus 2. I'm having troubles here, and I've messed up the first one. Let's start over, just to make sure that I do this right. This is where the errors in these problems can happen, because there's so many steps. All right, this looks better. 2a minus 2 minus 2a minus 2h plus 2, all over h. All right, now we're to the canceling part. But all over h times the quantity a plus h plus 1 times the quantity a minus 1. Okay, now we can cancel. 2a and the minus 2a and the 2's are gone. The h's are gone. So now I have the limit of h as it approaches 0. Let me clean this up so we can see what's going on here. We have negative 2 left on the top. And then we have on the bottom a plus h plus 1 times the quantity a minus 1. And we can sub in our 0 now. So we end up with a plus 1 because the 0 in the h position is just going to be gone. So, and then a minus 1. So now this is our derivative. So if we had some sort of value we needed to plug in, we could plug it in for the a value, and then it would spit out some other number that we were looking for, whether it be a velocity or some other rate of change thing or something. So, but that didn't give us anything about anything else other than just find the derivative. So here you go. There's the derivative. Doo -doo -doo -doo. Clean this up a little bit so it looks a little better. All right, there we go. So we have negative 2 and then a minus 1 squared. And that has a really dramatic division sign. There we go. Box that guy up. Ship it. We're all done. That's the last of this chapter test review. So good luck to all of you. Hopefully this video has been helpful. Again, I encourage you guys to try all this on your own. Oh, my penmanship is terrible. This all looks terrible. Let's try this again. All right. Good luck. All. So anyway, like I said, try and do all these on your own, and then just use a video as reference. Don't put it in place of your own personal studying. Excuse me. If you have any questions, please feel free to leave them in the comments. Like and subscribe. That way you'll see as soon as the next video goes up instead of waiting for our instructor to release the link. That's about all I can think of right now. So see you in class. Talk to you later. Bye.